Good morning and welcome to chemistry. Today we're just going to start right off with chapter 1, which is all about matter and stuff. We're going to talk about elements, compounds, mixtures, different kinds of elements, different kinds of compounds, different kinds of mixtures. What is the difference between stuff and mixes, and how can you tell what is one thing versus another versus stuff versus mixture? We're going to talk about all this. Why do we got to talk about matter? Because everything is more, like in the universe, is made out of matter. So that's really what we're going to do. And our goal for the first two parts of this chapter are basically to dig into and really split hairs about definitions of words, right? Because when you're out in the regular old world and you use words like stuff or thing or like mixture, it can have one meaning, but when you're in a science lab, we need to be very careful about what those words are, because every profession sort of has their own unique lexicon or like set of words that are very, very specific to that thing, and that is what we are going to dig into. Some of the things that we need to like really be aware of when we start talking about chemistry and atoms and electrons and stuff. All right, so very first thing that we're going to talk about is this: matter. This is the stuff that we want to talk about. Why do we want to talk about matter? Oh, look, wait, here's a word right there. That word is underlined and is probably going to be something kind of important. So you should know that anytime you see a word that is like underlined like that, that usually means that it's going to be kind of important for us, okay? So this is something important. That's a vocab word. So the definition of matter is anything that takes up space and has mass. So that's basically like stuff. Almost everything you can think of, except for things like energy. Energy doesn't take up space and doesn't have mass. Neither does light. It doesn't have mass, thank God, because it hits us at the speed of light, and if it had mass, that would be bad. So matter is anything that takes up space and has mass, which is different than a substance. A substance, on the other hand, is matter that has a uniform. Well, that was unexpected. So a substance is matter that has a uniform and unchanging composition. Now these are like some specific words. Uniform means the same, right? Like a military uniform. Everybody looks the same. And unchanging composition. In other words, when we set down a substance, it remains that substance. You get a block of, I don't know, what's a substance? Sugar? Great. You have a big sugar cube. If you put it on the shelf, it doesn't spontaneously turn into a banana, right? It just is what it is. But again, specifically speaking, that is what a substance is, because there are some things you can put up on a shelf and it turns into another substance. So, there's that. So matter is anything that takes up space and has mass, and a substance is I guess you could call it a specific kind of matter with its own specific and unique properties, right? Well, I guess the question is, how do you tell one substance from another? Well, this is how. From the properties, right? I mean, that's how you tell a duck is a duck, an apple is an apple, and a piece of chocolate is a piece of chocolate, right? You tell by its properties. So there are two basic categories of properties. This first one that we're going to look at right here, this is called physical properties. Now, the thing with the physical property is that you can measure a physical property without changing the thing that you are observing. So I pick up a duck. I look at the duck. It looks like a duck. It is still a duck by looking at it. You know what I'm saying? Therefore, it is like that's a physical property, what it looks like. I smell the duck. It smells, I don't know what ducks smell like, ducky, but I haven't changed the duck. Now, if I light the duck on fire, we're not really going to have a duck anymore. So let's not do that. Let's change our example. I don't want to light a duck on fire. So what if you had a piece of paper? Okay, you look at a piece of paper. It's white. You light the piece of paper on fire. When the fire is done, it's no longer a piece of paper. So that cannot be a physical property, right? You cannot change. It's without changing what you are looking at, what you're observing. That's how we know that it's going to be a physical property, right? And so some really common examples of that are density. That's why you guys have hammered density since 8th grade. Mostly because this is a physical property that you can't just see. You have to do an indirect measurement, right? It takes mass and volume to get density. But, color, you look at it, stays the same. Taste, you taste it, it basically looks the same. But here's a new one for a lot of people. melting and boiling. Not so much the melting and boiling point, but just melting and boiling. Here's the deal. If you take ice, right? Ice is made out of H2O. It's just in solid form. If you melt ice, you now have liquid water. It's still H2O, just liquid. You guys picking up what I'm putting down? Riding the waves? Yeah, riding the waves. Anyway, also you take liquid water and you heat it up even more and it boils. It turns into a vapor, right? It turns into a gas. It is still H2O. The only difference is that in a solid, those particles are like this. In a liquid, they're like, well, they're not really like, they're more like this. They can like move around and whatnot. And in a gas, they're just like all over the place, right? So the distance between the particles is the only difference between a solid, a liquid, and a gas. Still the same thing. So phase change, in other words, going from a solid to a liquid to a gas, phase change is a physical change because you can take steam, condense it down to water, and freeze it back into ice. It's all the same stuff. Do you understand what I'm saying? Picking it up, putting it down. Yeah, good. Okay, so that's a physical change. Or a physical property, I mean. Sorry, I said change, I meant property. What I said, scratch that. Anyway, moving on, there are, fun fact, 2 kinds of physical properties. One that we're going to look at here is called extensive. Now, an extensive property, I want you to look at that X. That's like exit or like outside, like exoskeleton, like on the outside. So an extensive property is kind of on the outside, if you will, like philosophically speaking, of the thing. So really it only depends on the amount of sample that you have, okay? So that would be like size, that would be like mass or shape, something like that, right? That's an extensive property. And it can change, right? So you can have like 10 pounds of copper, you can have 2 pounds of copper. The mass, right, changes based on the amount of copper that you have. Now the other one, this one, the intensive property, this is like internal. It is a fundamental basic property that cannot be changed no matter how big or little piece you have. For example, copper conducts electricity. It does not matter if it is a big piece of copper or a small piece of copper, it conducts electricity. Copper is the color of copper, right? Because it's copper. So it doesn't matter if you have a giant sheet of copper or like a little teeny penny, the color is the same. That is an intensive property. In other words, it doesn't matter what size the sample is, you have the same color copper of copper when you have copper. Dig? Good. Great. Do you see so far? I'm just gonna like point this out so you guys can like dig it, like really like I want you to focus in onto the important part here. The point of this, we're getting into some really detailed vocabulary, right? Because we need to know the difference between extensive and intensive properties. Why? Because we're gonna be chemists here today, people. So we need to know that difference. And again, first couple of days, it's gonna be all about vocab, right? Awesome, because the next kind of vocab we got is right there. Chemical property. Now, this here chemical property is going to be a little bit different than your physical property because it's to observe a chemical property, you have to change the thing that you are looking at, right? It will change into another substance. And when I say change into another substance, I mean completely different. Totally different, right? Yeah. Like, let's go back to, well, I don't want to cook a duck, so let's just stick with paper. If you start with paper, a chemical property would be flammability. I even have it right here, flammability. So flammability is a chemical property. When you are done observing the chemical property, you no longer have a piece of paper. You have like ash, you have heat, and a little bit of water vapor. Like that's it. Like it's gone. No more paper, right? Same with like the flammability of a piece of firewood. Well, you only really get to observe that once. You know what I'm saying? Oh, taste of coffee, physical property. Beautiful. Love it. Intensive, by the way. It doesn't matter if I take a big gulp or a little gulp. Taste is taste. Anyway, back to chemical property. Right, reactivity. Like if something reacts, like copper reacts with oxygen, right? So that's going to be a chemical property. How do we know? Because it's no longer copper after it reacts with oxygen. Like the Statue of Liberty started out like, you know, shiny and coppery, but over time it has reacted with oxygen in the air and the water and has turned that beautiful like light limey green color. That's reactivity. Also, this other thing down here, heat of combustion. This is another kind of property that we're going to be digging into a lot more later on in the year, But this is another example of like an indirect property. You cannot directly measure the heat of combustion. You can't look at something and be like, wow, it's got like 50 BTUs in it. You have to measure it, right? So how much heat energy is contained in our food, the only way we know is you have to burn it. Like if you want to know how many calories are in a potato chip, you have to burn the potato chip. You got to get that energy out of it, right? Heat of combustion, how hot something burns. And we can't, a lot of people know this by different firewoods, right? Like oak puts off a lot of good heat in your wood stove, but you know, something like pine, not so much heat because it doesn't have it doesn't contain that energy in there. That's what heat of combustion is, right? Chemical property, and it is a chemical property because we cannot measure it without changing the substance that we are looking at, right? So, like I said, every substance has its own unique properties. This is how we know a cute little duck is a duck. That's how we know an apple is an apple and a frog is a frog instead of a toad. And I know it seems kind of silly, but really, that's it. I mean, it's the same thing that happens in your everyday life. Like the exact way you can tell a duck from an apple is how we can tell substances apart. The only problem here in chemistry, like in particular, is that most substances, or many substances, look exactly alike. Like most gases are clear, and you know they're gases, so you can't really tell just by looking at them. Most salts or substances are also just a crystalline white powder, like potassium cyanide, a white crystalline powder. Table sugar, a white crystalline substance. Table salt, you know, like stuff you put on like French fries, a white crystalline salt. So it can get, we in chemistry, we're going to use some properties that are not commonly seen in everyday human life. That's why sometimes chemistry can be a little bit weird. But the same ideas in real life apply to chemistry. It is as obvious as looking at a duck versus an apple, just the properties tend to be indirect properties. So instead of just looking at it, you might need to like do a couple measurements to find out what those properties are. Dig? Dig. Let's move on. So before we get too far, I want to review with you guys what the states of matter are, because again, we're talking about matter. And for us, we're going to have we're only going to focus on 3 phases of matter. Are there more? Yeah, but are we going to talk about them? No. And this is stuff that you know from like way back then. Solid, it has definite shape and volume, but what I really want to like hone in on and see that is different for us is that the particles, see, we are looking at everything from the perspective of particles in chemistry. The particles are held in place, but they still vibrate. They're like kind of like buzzing around. It's like the kinetic energy of everything. All matter has kinetic energy. All particles are constantly moving and buzzing and like bouncing around. Solid, they're fixed in place. In other words, they don't like move around. They're like these internal forces that hold them in place. They're still kind of going, but they're stuck. Okay? Great. So, this thing over here, this is silly, but it is what it is. This is a particle diagram for a solid. Why? And I'm just going to go over this real quick because often this is like how standardized tests happen. You'll see it. It's silly. Of all the time that I've had working as a chemist, I've never done any of these. But here we are in academia. So what this is a picture, and each dot here represents an atom. And if you'll notice, for a solid, it makes a shape, its own sort of shape. And each particle is touching another particle. They're all making contact, right? They're not all flowing down to the bottom like a liquid would, and they're not all flying all over the place like a gas would. Got it? Great. Moving on to a liquid. So liquids, here's a fun fact, they have constant volume. In other words, you can't really compress a liquid, and it takes the shape of its container, which is awesome because then we have hydraulics and front end loading excavators that go and like do amazing amounts of work like that. Because the way hydraulics work is you have an engine that just squeezes liquid, right? But since it can take the shape of its container, if its container is a tube, the liquid just spurts around in a tube and goes into a cylinder that expands out, makes the excavator and arm go like that, and the forces are unbelievable because you're using a diesel engine to do it. And it can't be compressed. It's not squishy. That's why all the force from the engine can be like directed into the like scoop of the excavator. You guys dig what I'm saying? So, fun fact, since most of you guys are either beginning to drive or will be soon, here's how brakes work. Right? When you press the brake pedal, just on the other side of like your firewall in the like engine compartment, there's a big round disc. And that is called the master cylinder, and you step on that, and that cylinder squishes liquid, brake fluid, which is basically hydraulic fluid, through some tubes. And that hydraulic fluid goes down, wiggling all through the tubes, and it comes out to these clamps, and then it pushes a little cylinder that makes clamps go that squeeze onto the disc that's stuck to your wheel that's spinning. The clamp squeezes and it slows down. Yay! And it's an amazing amount of force that can be applied because all that force is sort of like amplified from the master cylinder to your brake pads and blah, blah, blah. But the force is transferred directly. So the harder you step on the brakes, the harder those clamps clamp. Unless you live in the North Country and you go through winter. And it goes from like 90 degrees in summer to like minus 5,000 degrees in winter with salt everywhere. The salt erodes things, and what can sometimes happen is a little bubble of air will get in your gas lines. And when that happens, you step on the brake. The brakes are all squishy because gas is squishy, but liquids aren't. So what you need to do is you step on the brake, and it takes that bubble and squishes it. You let go, you step on the brake again, it squishes it again. You let go, you step on again, and it squishes it again until you can finally get your brakes to start to work. When it happens, pull over, call someone, don't drive anymore. Losing your brakes it's not great. Trust me. I know this. I'm telling you because I know. Pull over and call someone. It's not good. It's not a good time. It's not a good time. But liquids are awesome because of this, right? So on the particle level, the particles are in constant motion again, but they cannot break away from one another. So the difference between the solid and the gas is the solid is locked, stuck right in place, but a liquid, they can kind of move and roll around past each other, right? So if like one comes over here, it can like fall over down that way, but it still sticks, right? They all stick together. And so the particle diagram for that is going to look like this. We've got little things, little particles. They're kind of touching each other, but what's key here is that it fills the bottom of the container because that's what happens. Gravity pulls everything down, so everything goes down, but they can't quite separate. You dig what I'm saying? Now you add a little bit of heat, and here you go, gas. It fills the entire container. The particles are very far apart from one another. They will fill the entire box, and they, technically speaking, don't really interact with one another. And for our purposes, we're going to pretend like they don't. In reality, do they interact with each other? Yeah, but it's not something that we're going to worry about in our very first chem class. How about that? Let's wait for a little bit before we get into that kind of nastiness. So another little detail about words is vapor. So we will often hear things like hydrogen gas. You will not hear hydrogen vapor, but you will hear things like water vapor. And the reason why is because water, under normal conditions, is a liquid. But if you boil it, it turns into a gas. So we call it water vapor. So vapor is the gas state of something that is not normally a gas, right? So you'll hear about mercury vapor, or you can even get iron vapor if it's hot enough. I mean, you can boil just about anything, really. So that's what this word means, vapor. Different than gas. Right? See, little teeny details, big meaning behind them, though. So changes in matter, changes between solid, liquid, gas, going from one substance to another, all that kind of good stuff. First is physical change. This is where, a physical change does not change the substance or its composition, just like a physical property. You can observe it without changing it. A physical change doesn't change the substance, right? This is like folding a piece of paper. You're changing the shape, physical change, right? Like I said before, phase change is a physical change, right? Boop. Phase change is a physical change. Solid, liquid, gas, right? The particles are like held together. This is what a solid looks like. This is what a liquid looks like, where like they're still kind of held together. And then the gas, they're like all over the place. They're just all like totally separate and whatnot, right? So phase change is a physical change. Ice is water. Water is water. Steam is water. Also, fun fact, dissolving is a physical change. I don't know if you guys know that, but dissolving is definitely, wait, hold on a second. Dissolving is definitely a physical change because if you think about it, if you take sugar and water, you start out with sugar. It's sugary and delicious, and water is refreshing and liquidy. And when you dissolve sugar in water, you get a refreshing, liquidy sugar substance, like mixture. You dig? So the water hasn't changed. It's still watery. The sugar hasn't changed. It's still sugary. It's just been dissolved or broken up, atom by atom, molecule by molecule, and that's why we can't see it, because it's disappeared. Do you guys dig what I'm saying? So the next thing I want to talk about, that shouldn't be there at all, is chemical chains. Let me go like this for a second. There. And this shouldn't be up here. These Man, these guys. Ready? Watch this. That's right. Don't mess with the stew. I've got a delete button. Yeah, mistakes are going to happen, guys. Let's just buckle up and get used to it. Lord knows I'm used to mistakes by now. And chemical change, this is a change where you end up with a brand new substance. And when I say a brand new substance, I mean the new substance has different properties than the elements that make it up, like wicked, total, completely, utterly opposite. The example that people love to use in chemistry classes everywhere is hydrogen, oxygen, combining to make water. Now, hydrogen gas is a ridiculously explosive gas. I give to you the Hindenburg. If you don't know what the Hindenburg is, go to YouTube and look it up. Hydrogen burns, dude. Like, come on. And oxygen, if you don't know that oxygen burns by now, I can't help you. But oxygen burns. However, if you put oxygen and hydrogen together in a 2 hydrogens to 1 oxygen ratio, you have water, which puts out fires. So, right? Anyway, yeah, a compound, a chemical change, changes it utterly, completely, and totally. I cannot overemphasize how different the new substance is. Does that make sense? But during that chemical change or physical change, any kind of change, matter is never created or is it destroyed. Never, ever, never, ever. So put this in your noggin for a minute. If you burn 50 tons of firewood or like 100 gallons of gasoline, that exact same mass of matter still exists because you're taking firewood and you're taking oxygen and you're making a new compound. You're taking gasoline, you're taking oxygen, and you're making a new compound. Do you understand what I'm saying? It doesn't magically disappear. Even if we can't see it right in front of us, it's there. So the mass of reactants, always, like this is always, the mass of reactants or the things that go into a chemical reaction will always equal the mass of the products, or that means like this, like the things that are produced in a chemical reaction, right? Reactants react, the products are produced. It kind of works like that. Okay? So the mass you start with is always equal to the mass you finish. If you have 5 grams in the beginning of reactants, you will have 5 grams of products. End of story. You can't magically disappear stuff. Harry Potter doesn't happen in real life, unfortunately. And the next thing I want to talk about are mixtures. Okay, so we had the pure substance, right? Substances. Like chemical properties, physical properties, chemical change, physical change, solid, liquid, gas, because that's kind of how substances show up. We get 3 versions of substances. And then the changes, that's how they're the properties. That's how we can tell them. I tell them apart. Like either you mess with it and you don't change it, you mess with it and you do change it. Like the changes in the properties are pretty well intertwined there. But stuff can be put together. Okay, so a mixture. A mixture is 2 or more substance. Wrong kind of or. 2 or. Man, hold on. I can't let that go. All right, I feel better about myself now. Okay, so it is 2 or more substances put together. Okay, did I say that they react? No, they do not react. It is 2 or more substances put together like in a container. So you could have a container of, I don't know, what do you guys want to put in a container? Let's put bicycle wheels and apples. So you have a mixture of bicycle wheels and apples. That's weird, but that's a mixture, right? Nothing happens. They just sort of sit there. That's what a mixture is. The bicycle wheels are still bicycles. The apples are still apples. That's a mixture. You guys get what I'm saying? They just occupy the same container. That is by definition what a mixture is. So when we have the word mixture coming out of our face, what we're saying is that those 2 substances are not reacting. Nothing's happening. They're staying the same. They're just in a mixture. Like a mixture of salt water. Right? Salt stays salty, water stays watery. A mixture of sugar, water, sugar and water. Sugar staying sugary, water staying watery. Lovely. Dig, dug, awesome. Now, 2 kinds. Because there's never just one. There's always got to be more than one kind. And the first kind we're going to look at is heterogeneous. Now, heterogeneous, I want you to dig in and get your English caps on and look at this prefix hetero. Hetero means different. Genius means made out of, right? Like Genesis from the Bible and hetero from, words. It means different, made from. It's made from different things. And for us, we can see them, right? So a heterogeneous mixture is not blended smoothly throughout. We can look at it and we can see the different parts with your eyes. That's it. Now you can get as complicated as you could possibly get. There's all kinds of weird outliers. Every time there's a rule, there's like 1,000 like exceptions to it, or like weirdnesses or things that blur the edges. Always in nature. Always. There's never like a black and white rule in nature. Never. So we are sticking with things very easy, right? Like granite. You look at a piece of granite, you can see the bits and pieces of the flakes. That's a heterogeneous mixture. How about sand and water? Let's call that a heterogeneous mixture because you can see the sand and you can see the water. Rice pudding. I love it. You might not like it because you never had good rice pudding, but you can see little chunks of rice and you can see little chunks of pudding. I don't know, like anything, like whatever you want to do. The bicycle wheels and I don't know, what was that? What else? And apples. That's a heterogeneous mixture because you look at it and you can see the different pieces and parts. You guys get what I'm saying? Great. Moving on. The next one is homogeneous or homogeneous, however you want, tomato, I really don't care. But this prefix, homo, means same, right? Like Homo sapien, same species. That's us. It's like a Homo sapien is the same species. Again, genus means like what it's made of. This says homogeneous. It looks like it's made of the same stuff. It is blended smoothly throughout. It looks like it's the same thing. When I say constant composition, what I'm saying here is that it's like it looks the same. Right, so if I had a little beaker of something with constant composition and I plunked a straw in it there, I'd get the exact same sample as if I plunked a straw in down there. You guys get what I'm saying? That's what I mean by constant composition. Constant throughout. Looks the same throughout, like milk, water, jello. I don't know, you can come up with like a million different ways of, or examples of homogeneous mixtures. Separating the mixtures. That's what we're looking at next. And there are a few versions. These are the 4 things that we are going to look at. Filtration. My favorite because it's how I make coffee. It separates it by size, right? You have water, you have coffee grinds, you filter out the coffee grinds based on size. The next one is distillation. Now, a distillation. You guys see this? Still? Have you guys ever heard of still? From your history class back during Prohibition when people would like make moonshine back in the woods because they made alcohol illegal, and so they made a still, which is a distillation apparatus, right? And water and alcohol, drinking alcohol, there's like a million different kinds of alcohol, but the one kind of alcohol that we can drink, not the others we can drink, they will all kill you or make you blind. But the one kind that we can drink has a boiling point of about 60 degrees Celsius, and water is about 100 degrees Celsius. So if you have a bunch of grapes and they get all like fermented and stuff, back in the day, it was like illegal to have wine. So when they needed to get the alcohol from one place to another, instead of having these giant 50-gallon barrels of wine, they distilled it, or they separated the alcohol out of the water. They heated it up to about 60 degrees so all the alcohol could boil off, and then they condensed it, put it in a teeny flask, and then a 50-gallon barrel of wine could be shrunk down to a little jug, and they could bring that to the city and make lots of money, just like, you know, illegal drug trade. Just it was alcohol back then. The other one is chromatography. So there's filtration, separating by size. Distillation, separated by boiling point. And then we have chromatography. Now, this is a kind of a weird one, but this is how we separate things based on the tendency to move across a medium. I know you did this with Krekel the other year. Where you take ink and you can like dip it in some solvent and the ink spreads across a piece of paper and you see all the different pigments that go in it. This is how we do all of our drug testing, and the vast majority of our like chemical analysis is done with some version of chromatography. You can get a PhD in just chromatography if you want. And the only thing we do is we use a different medium. Like if we want to test an athlete's blood for dope or something, we just grab a little bit of blood, put it into the apparatus, we move it across a substance that can separate blood into all of its parts, and we wait for that one little part of dope to come out. And if it doesn't come out, you're good. If it does, we got you. You dig? And the last one, crystallization. This one, when I worked in pharmaceuticals, this is the one that we used quite often. It's how we make really, really pure substances. Because as the samples crystallize, you have one molecule, the next molecule lines up, and then the next molecule lines up, and the next molecule lines up. And as it does so, it pushes everything else kind of out of its way. kind of like making rock candy, right? Or like the chunks of sugar at the bottom of maple syrup. I don't know if you've ever noticed, but if you rinse that sugar off, it's perfectly clear. There's no brownness or anything, because as those sugar molecules crystallize, it pushes out all the minerals and stuff that make maple syrup brown. Dig? Dug. Oh, hey! You made it to the end of your first like stew video thing, Bob. You want to get? So the homework that we've got is going to be the matter homework, which is going to be the first one in your homework packet. Good day, good luck. What a pleasure talking to you. Yeah, welcome to Chem. Hold on tight, because we're just getting started.